Basically, what I'd like to do today is to try to cover an enormous amount of work that's gone on in the area of surfaces and interfaces and polymers. And to do that, in any real sense, I have to make obvious selections. So what I've done is to try to talk about this by thinking what are the special qualities of polymer surfaces and interfaces that are real, from the point of view, they're polymeric, that really are different from small molecule surfaces and interfaces. The main feature, I think, here is the fact that the effects of surfaces and interfaces are remarkably long range in these materials. And what I want to do is hit a number of different milestone experiments that illustrate this fact. The second point that I'd like to make right at the beginning is, and Bill Gressley made this to some extent, is our dependence in this field on other branches of physics. All right? You might say, well, polymer surfaces and interfaces are quite fashionable and very interesting right now. Why did it take until 20 years ago, all right, for this field to start to emerge? And the reason is that the tools we need to study polymer surfaces and interfaces really only emerged rather recently. And they emerged not primarily from other parts of physics. And I'd like I picked my examples to try to illustrate that. Okay, the 5 examples I'd like to talk about here are listed. Right, and with each of these examples, I'd like to illustrate a particular instrument that's really made the advance possible, or a technique that's made the advance possible. So without any further ado, let me start with my first example, which involves the forces between polymer brushes in solution. Now, polymer brushes in solution, essentially these are polymer molecules that are somehow tethered to solid surfaces. And this interaction between two such surfaces has very important applications, right, particularly in stabilization of colloids, right, in the whole area of adhesion, lubrication, chromatography, biocompatibility. You can name just lots and lots of different applications of this. The important tool which came along, all right, and was adapted by the polymer physics community, but it really arose first in the fundamental study of surfaces and liquids. From the point of view of the group that was interested in this, was interested primarily in lubrication, right, is the surface forces apparatus, where two mica surfaces, atomically smooth, can be brought together with control on the order of an angstrom. All right, and with being able to measure this spacing and be able to measure the forces between them. Now, these forces between polymer brushes, we need some way to get the polymer brush structure to begin with. And the first approach to this was taken at the University of Minnesota, where they used block copolymers, all right, which had a hydrophilic block which attached to the mica, and a hydrophobic block which was swollen highly in toluene solutions. And what you see here are some of the first measurements, all right, measuring the force divided by the radius of these mica sheets, the radius of curvature of the cross-cylinder arrangement. This parameter turns out to scale to be directly related to the energy versus distance curve for these brushes. And the remarkable thing that you can see here is the very, very long-range nature of this interaction. The radius of gyration of the polystyrene molecule in solution is much, much smaller than this. So immediately, this measurement showed us that these brushes had to be extremely stretched. And that agreed with previous theoretical approaches to the problem, which I'll talk about in the next couple of slides. The next advance came by making brushes of completely end-anchored chains. All right, and this was made essentially by making a zwitterion end to a polystyrene chain. And now this group took up very little space on the surface, so it didn't have to worry about the footprint of the other block of a block copolymer. And this just shows two different molecular weights of the effects of two different molecular weights of the polystyrene chain. The force versus separation curves. All right, you can see the enormous distances. Here, the radius of gyration of this molecule, all right, in a theta solvent is about 43 angstroms. The forces between these plates are beginning to be felt at 400 angstrom separations. Similarly, here, the radius of gyration, all right, in the unswollen state is about 164 angstroms. Here we can begin to see that effect at well over 2,000 angstroms. Right? This is a prime example of how in the polymer cases, all right, where the very long-range nature of the interaction between polymer layers becomes apparent. Now, right, it turns out to be possible, using a scaling approach, to completely superimpose all the data on all different molecular weights. All right, this is a master curve, essentially taking the separation and normalizing it by a distance of the initial approach, and by scaling the force radius portion, all the data fall on the same curve. All right, remarkably, this L0 scaling factor depends on the molecular weight to the 0.6 power, exactly that Flory exponent. And the comparison with the theories, which were done, at least the first of these by Alexander and de Gennes, was done considerably before the scaling theory was suitable without worrying about prefactors, does a wonderful job of fitting this. So does the later theory, the parabolic brush, all right, by Milner, Witten, and Cates. Right? For these types of experiments, it's hard to distinguish between the scaling theory, which assumes a brush which has constant density throughout a certain thickness L0, and this one which assumes where the calculations show should have a parabolic shape. That's the first of my examples of this action at a distance. The second example also picks up a long-standing theoretical calculation, and that Bill Gressley alluded to a little bit, and that is the importance of the Flory interaction parameter, all right, in immiscible polymer systems. All right, it was well back in the 1970s, Helfand and Tagami did a first theory of the volume fraction versus depth profile across a polymer-polymer interface. Polymer A on this side, polymer B on this side, and showed theoretically that this should not be an abrupt interface, but there should be a gradient, a tangent, hyperbolic tangent type profile of this sort, where the width of the interface should scale as the statistical segment length divided by the square root of the Flory chi parameter. Now, this theory also predicted the dependence of the interfacial tension, gamma 0, on chi. And it should go like the square root of chi. And in general, there are very, very few methods of measuring the Flory interaction parameter for immiscible polymer systems. And as Bill suggested, the great majority of these systems are, in fact, of all the polymers pairs that we can think of, are, in fact, immiscible. So it would be a great advantage if we knew that we could measure the interfacial tension and immediately get chi and that this was an accurate formula. But we need some way to check that. And so the obvious way to check that was to somehow be able to measure, this interfacial width and see whether that worked out. The problem is that for a number of systems, I'm just showing you an example for the deuterated polystyrene PMMA system, where the theory predicted about 30 angstroms from measurements of chi using black copolymers, as Bill suggested, and measurements using neutron reflectivity. The initial measurements showed numbers that were almost double that, about 50 angstroms or so. So there was this strong discrepancy. And of course, many ideas came along to try to explain this discrepancy, but the most obvious one was to think about the possibility of capillary waves. After all, if we did not have these layers in a thin film, there's no reason to think that we would necessarily end up with completely planar interfaces. It turns out that the amplitude of the capillary waves on such an interface can be predicted, as would be measured from a neutron reflection experiment, which averages over some region of the interface. It should go like the predicted width squared here. There should be some lower cutoff length, if you like, corresponding to the actual width of the interface. But there should be some upper length here involving the lateral coherence of the neutron beam. But more importantly, this very recent paper pointed out that there is also a tendency for this interface to become pinned in the middle of any thin film, due to the van der Waals interactions, across here. If this is, in fact, a stable pair, the van der Waals interactions will tend to repel this interface from either side, either the substrate or the surface. And that contribution goes like this. It goes like the film thickness to the 4th power in this logarithm. So in principle, one should be able to measure what happens. And notice that as the film gets thinner and thinner, this term goes toward 1, and we will essentially quench the capillary waves. In fact, that was just showed by a whole set of beautiful neutron reflection experiments from polystyrene PMMA bilayers of different thicknesses. The thickest is over here. You can see all these oscillations coming from the interference, and you can see that as oscillations die out at a momentum transfer length about here, or vector about here. We see as we go to thinner and thinner films, those oscillations appear and go out much further in Q space. What that means is essentially that the interface that's being measured is getting narrower. And the results of these experiments show I think very nicely the effects the capillary waves, and the effect of making the films thinner and thinner. Essentially, this interfacial width decreases. You can extract now a value which is now actually below the self-consistent field theory calculation. And there are still things that are not taken. This still needs work theoretically. All right, there's still things that are not taken into account. For example, the physical surface is assumed to be absolutely flat, which of course it isn't. It has its own capillary waves on it. Okay, now I want to shift to another area. So this is a second case where the interfacial widths are much larger than the monomer sizes. I want to shift to a third area, and this has to do with the whole area of block copolymers that Bill introduced, right, and the idea of self-assembly. And I'll just introduce this with one very recent application of using block copolymers as templates for nanolithography from the group at Princeton, showing very beautiful transfer of a pattern in a block copolymer film into a semiconductor substrate. So perhaps we can give something back to physics, the rest of physics as well. Well, my story here starts out with, again, some very nice neutron experiments, all right, where this is a film that's been annealed of polystyrene and deuterated PMMA, all right, on a substrate of silicon. All right, you see a fit to the neutron reflection. You see the whole series of beautiful spikes here corresponding to the lamellar structure of this block copolymer, which I'm showing here on the bottom in the cartoon. All right, with a layer of the PMMA against the silicon oxide on the silicon, and a layer of polystyrene on the top here against the air. All right, very wonderful stacking, all right, observed dramatically, all right, with neutron reflection. Now, of course, that stacking, can only, you think about this for a minute, you realize that such a stacking can only exist with a certain thickness of film. All right, and it turns out that there is a quantization condition imposed by the structure of the block copolymer. If I have a thin enough film, all right, and instead of making this 1.5 N.5 lamellae thick, I make it some amount over or under that, I will get islands and holes. And then that was a beautiful set of initial observations, all right, shown here. All right, starting with a film which was absolutely flat after being spun cast on annealing, all right, transforming itself into this layered structure, but having a little bit, not quite enough of the block copolymer, all right, and ending up with some holes in the top layer. All right, that's spawned an enormous activity in this area to try to use this for patterning purposes. All right, and that's also an example of this very long-range effect of the interface, in this case, the bottom interface. What I want to come to next, though, is looking at what happens for a disordered block copolymer film. All right, same polystyrene PMMA film. All right, neutron reflectivity, and what this is showing is the fact that to get a decent fit, all right, for this disordered case, this particular line right here is the fit that you would need, or what you would get for a film which was uniform in concentration of deuterated polystyrene. In fact, what you need to get a good fit is something that looks like this, with a deuterated polystyrene layer almost, not quite, about half pure at the surface, and a sort of dying oscillation into the bulk. It's one starting from the interface with the silicon oxide, all right, and dying that way, all right, and yet this is completely, in the bulk, is completely disordered. All right, these effects occur over very large distances, corresponding even to the molecular weight of the of the molecular size of the block copolymer. And I'll show you that on the next slide. As one approaches the order-disorder temperature, this surface effect on ordering, all right, can propagate very large distances. All right, shown down here, all right, this is at above the order-disorder temperature. As the order-disorder temperature is approached, you can see that oscillation growing in. All right, eventually the film becomes completely ordered. You see the Bragg peaks. All right, this is just these distances here. All right, as you approach the order-disorder temperature. Clearly, the inner faces in these thin films are having a huge effect over distances that are extremely large, not only compared to the polymer segments, but compared to even the sizes of the molecules themselves. All right, this is one other interesting fact, is that the order-disorder temperature in such thin films now changes with film thickness. All right, as you make the film thinner and thinner, all right, that order-disorder temperature goes up by as much as 10 degrees or so. Okay, the last two applications I wanted to describe to you involve polymer blends that Bill mentioned. And it actually picks up this theme of both of the previous speakers about the new polyolefins and how to deal with these. What I'm showing here is a phase diagram for a mixture of two random copolymers, which happens to be a useful way to sort of study this effect. All right, this one is a random copolymer of polyethylethylene and polyethylene, all right, with about 86% of the polyethylethylene, all right, and that's being mixed with a random copolymer of polyethylethylene and polyethylene, which has 75%. All right, they're both about the same degree of polymerization. One is labeled with deuterium, but sparsely enough that it doesn't affect the thermodynamics in this system. We don't have to worry about any isotope effect. The phase diagram in this system is determined by actually measuring in a film, by measuring the two coexisting compositions. It turns out that the one with the more ethyl branches is attracted to the surface. But the data that I want to show you, the results I want to show you, correspond to these fairly dilute mixtures over here, which are mostly the H75 and have a little bit of the D86. So they are in the one-phase region, but what we're going to see is that the surface of this material, all right, strongly attracts this component, and we build up layers which can be quite large. All right, the technique that I want to pair with this is an ion beam technique called nuclear reaction analysis. All right, again, this did not originate in polymer physics. It originated really in the nuclear physics community, but it turns out by using a helium-3 beam, all right, this will react, these nuclei will react with deuterium in the sample to produce a proton and an alpha particle. And a large amount of energy. If one detects the proton with a backward detector, one can determine very accurately the energy loss of the helium-3 going into the sample. And by this means, determine the concentration of the deuterated material versus depth. This happens to be polystyrene, but we'll be applying it to the experiments with the deuterated polyethylene copolymers. Right? The neat thing here is the depth resolution is first of all, it's a direct space technique. We don't need to do any modeling as in the case of neutron reflectivity. All right? And all right, we can see the resolution of the technique, which would correspond to a full width half maximum of under 100 angstroms. Now, so let's look at the surface enrichment in such blends. All right, and now I'm going to show you results from one of these temperatures, from the 130 degrees. As one starts far away from the coexisting composition, the area here that I've shown in like this. Underneath the peak is will be called the interfacial excess. All right, and notice that our length scales here are, again, very large, that we build up to layers which are of the order of 500 angstroms, all right, in size. Sorry, 50 nanometers, 500 angstroms at least in size. Again, surface interaction causing very large effects in terms of the segregation of materials. The surface excess versus the bulk volume fraction, again, we see numbers in the neighborhood of 200 to 300 angstroms, all right, as we approach that critical, as we approach the coexistence curve. And the surface composition, all right, starting with, let's say, a tenth volume fraction, all right, is in the range of nearly 100%. Okay, so let's go from that particular example to a final one, all right, which is what happens when you take a mixture of two polymers and quench inside, instead of being out here, and in this particular case, one of the polymers, the deuterated one, is actually attracted to the surface. This is a case, these are polyethylene propylene polymers. This is a case where the deuterated one is attracted to the surface. And instead of working in the one-phase regime out here, let's work inside, or quench inside the spinodal and see what happens. All right? Inside the spinodal, of course, normally what we would get is spinodal decomposition, and this is quite well known, where we would have a dominant wave vector. But this wave vector would be essentially random in direction. And so we would get the characteristic bicontinuous structures. We're going to do this in a thin film. And the interesting thing here is, again, the surface effect, the surfaces and the interfaces in the film have a remarkably long-range effect on the phase structure of the film. So to start with, this mixture is absolutely uniform, 50-50 mixture. All right, it's as spun. You can see the volume fraction versus depth profile. This particular technique that's used here is not quite the same as the nuclear reaction analysis, and it will allow us to measure both the deuterated and the protonated species as well, which is always nice. What you see in this particular example is what happens after 5 hours at 294 Kelvin, all right, at room temperature. You see these oscillating depth profiles develop, all right, over very large distances. All right, so there's a layer of deuterium-rich polymer, a layer of normal polymer, another layer of deuterium-rich polymer, and so forth. And eventually, this becomes uniform, all right, at 50%. What's going on here is that the surface attracts one of the components, the deuterated component, and that basically starts a spinodal wave propagating in from the surface. And that wave dominates. So the wave vector, all right, normal to the surface, dominates within a very large distance from that surface. One of the consequences of that, if you look at the behavior in thin films, all right, the consequence of it is that you can get interference. You can start a composition wave from the substrate, in this case silicon, all right, that propagates in this direction. All right, at certain film thicknesses, you get constructive interference. So there's a layer of deuterated polymer, protonated, deuterated, protonated, deuterated, protonated. All right, if you go to a thickness which is just a little bit smaller, all right, there's destructive interference. So you've got a layer of deuterated, protonated, all right, protonated, deuterated, but in the middle, the system can't make up its mind. over here, I'm just showing you some cell dynamic simulations, all right, for the same sets of conditions. You see they match very nicely to this kind of profile. And by the way, these were done with essentially no adjustable parameters. The diffusion coefficients in the system were known, and the thermodynamics in the system were known. And kind of the final slide on this just shows that out of these simulations, all right, which is becoming, as Bill said, a more and more powerful technique in polymer physics, one can get an accurate picture of what's happening laterally in the sample. All right. So, for example, this is the case where we saw destructive interference. So you have these layers of protonated, deuterated, all right, protonated, deuterated, and in the center, all right, it really cannot make up its mind what to do. All right. Okay. Well, I think my talk is really finished. I want to leave you again with the initial points that I made. All right, number one, in this particular area, I think the interest is really on the fact that the surfaces and interfaces have really long-range effects. And that's something that's really hard to achieve in small molecule systems, but happens really automatically in polymers. And that has all sorts of implications for trying to make structures by self-assembly and so forth, all the current buzzwords. The second point that I want to again leave you with is the fact that we are still very dependent on the rest of physics. All right, my advice to young people in this audience is to go to a lot of the other physics sessions, because you will pick up a new technique that you can bring to polymers. All right, and that may be the next breakthrough. Thank you very much.
In terms of long range, we're talking about quantitatively, how many radial gyrations of these polymers you're talking about? I mean,
well, in the case of the two surfaces in solution, the brush in solution, you saw there that it was of the order, these effects were occurring the order of 10 radii of gyration or more. In this last example, the radial gyration of these materials, these PEP and DPEP samples, is around 100 angstroms, a little bit more than 100 angstroms, and we're seeing effects over 5,000 angstroms.
Can you comment on the free energy density of the film where there's a constructive interference versus destructive interference in the last point you showed?
Yes.
Comment on the energy density, the free energy density. What thickness would be more preferred?
Okay, the free energy of the system seems to be well described from neutron scattering measurements that Frank Bates has made on these identical samples. It seems to be very well described by the Flory-Huggins free energy functional. All right, so that, in that sense, so I don't quite understand what you mean about.
What I meant is if you have two thicknesses.
Yes.
T1 and T2,
right.
In T1, the interference is such that it is constructive.
Okay. Yes.
Yeah.
Okay. Well, but what I should have mentioned is, of course, this is not the equilibrium situation. Okay. This is on the way to equilibrium. Okay. What you get in equilibrium is a single layer of the deuterated polymer on the surface, one polymer, and a single layer of the protonated polymer on the substrate.
But it is hard to reach that equilibrium.
Well, if you wait long enough, it actually comes in these systems.
Barry, last question. Why does deuterium go to the surface? What attracts the deuterium to the surface?
The attraction is essentially the same thing that gives you a chi in the isotopic chi, because what happens is that the deuterium carbon bond is a little less polarizable. Because of zero-point energy, the deuterium sits a little bit lower in the well, is a little less anharmonic. All right. For that reason, it's van der Waals energy breaking that bond is less, it's attracted to the surface. The differences in surface tension are extremely small, but they're enough to drive these huge effects in polymers.